Distant galaxies are not only receding from us, they're accelerating away from us. And dark energy plays a role in that, but not in the way you think. Hey crazies, dark energy is not some mysterious accelerating force. It's just a number, so forget about reality for a minute. Say we have a circle containing 2 dots. Now let's say the circle doubles in size every few seconds. That's a steady, constant doubling. In that case, the dots will accelerate apart. They'll be moving faster and faster away from each other. That's exponential growth, not constant growth. Exponential growth is constant growth for a universe. But I'm getting ahead of myself. That doesn't make sense unless we answer a couple other questions first. 1, what is dark energy? And 2, what exactly is the expansion rate? So let's get into it. We'll start with a common point of confusion. Dark energy and dark matter are not the same thing. They're not even called dark for the same reasons. Dark matter is a form of matter that, among other things, helps keep galaxy clusters together and affects the speed of the stars within those galaxies. It's called dark because it's literally dark. If you're interested, I have an entire video on how we know that exists. But the dark in dark energy isn't literal. They originally called it dark because it was shrouded in mystery. It's a metaphorical name. It shouldn't even be considered stuff. If you've watched any videos on dark energy before, you've probably seen a pie chart like this. This thin slice is all the regular matter and light in the universe. The next slice is all the dark matter. And the final huge slice is all the dark energy in the universe. Except dark energy shouldn't be on that chart. It doesn't clump together into objects. It doesn't even form diffuse clouds. It's not affected by gravity at all. Dark energy is uniform across all space and maintains a constant density across all time. As space expands, the total amount of dark energy increases in order to keep its density the same. That's ridiculous. How could dark energy know to do that? It doesn't have to know because it's not stuff that needs to know to do things. Dark energy is a property of space-time. That's it. Don't overthink it. I'd argue your confusion isn't a misconception about dark energy. It's a misunderstanding about expansion. To be clear, matter was not blasted apart at the Big Bang. It was not an explosion, so get that out of your head right now. If you absolutely need an everyday visual, the inflating balloon or rising loaf of bread will work in a pinch. But it's best not to use any analogies at all. They can and will get you into trouble. Just imagine what's really happening. The space everything occupies is growing larger over time. What we need is a way to represent that mathematically. And the obvious choice is the cosmic scale factor. It's defined as 1 in the present. That way the scale can be seen easily at a glance. If we measure it some other time and it's less than 1, we know the universe was smaller then. The opposite is true if it's larger than 1. This also means that expansion rates work in a way that's familiar. How the scale factor changes in time would be the expansion speed. A positive value means space is expanding, while a negative value means it's contracting. As far as we can tell, this number has been positive since the beginning of known time. Space as we know it has always been expanding. How that speed changes in time would be the acceleration. A positive value means the expansion is speeding up, while a negative value means it's slowing down. As far as we can tell, this number changed from negative to positive about 5 billion years ago. That is when the acceleration began. That doesn't tell us why, though. You're right, knowing when and how is not the same as understanding why. For that, we need a better measure of expansion. As it turns out, this expansion speed actually misrepresents the universe. Consider 2 galaxies, one twice as far as the other. That more distant galaxy is moving away at twice the speed. So measuring the expansion rate as a speed is object dependent and therefore not very useful. Thankfully, there is a solution to this problem. If the speed at which a galaxy is receding is proportional to its distance, this parameter is a better measure of expansion rate. It's called the Hubble Parameter. Right now, it's about 77 million kilometers per hour per billion light years. That means something a billion light years away is receding from us at 77 million kilometers per hour. And that'll handle any distance. Is the galaxy 2 billion light years away? Well, then it's receding at 154 million kilometers per hour. 3 billion light years? 231 million kilometers per hour. The Hubble parameter already has the distance factored in. It's 77 million kilometers per hour for every billion light years of distance. We could also relate this to the scale factor from earlier if we wanted. The speed is a dot, and the distance is just a. So we get a Hubble parameter that looks like this, which is much more useful. Now, let's bring it all together. The space everything occupies is growing larger over time. And as it grows, it carries all the regular matter, dark matter, and light with it. Basically, anything that can be considered stuff will also get more spaced out and therefore less dense. Dark energy doesn't do that. It isn't carried by the expansion. Remember, dark energy is a unique property of space-time itself. So naturally, if there's more space, there will be more dark energy. Its density never changes. Dark energy is pretty straightforward. There isn't a whole lot to misunderstand. So what's the problem, Smarty Pants? The problem is that expansion is counterintuitive. We want to measure expansion as a speed, but it's not a speed. It's a doubling rate. Remember how the circle doubled in size every few seconds? Well, now imagine the circle is space and the dots are just galaxies. It's the same phenomenon, just with a much slower doubling rate. What's the doubling rate of our universe? The Hubble parameter. I said earlier that it's about 77 million kilometers per hour per billion light years. But that's still thinking about this in terms of speed, which we absolutely should not be doing. After some unit shenanigans, the Hubble parameter is actually 1 over 10 billion years. Or in other words, the amount of space in the universe is doubling every 10 billion years or so. At least that's what it is right now. That doubling rate is still decreasing. Thanks to dark energy, in the distant cosmic future, the Hubble parameter will settle around 1 over 14 billion years. That's a constant steady doubling roughly every 14 billion years. But how does that make galaxies accelerate? Because of how numbers work. Consider this circle again. At some moment in time, these dots will be receding from each other at 10 pixels per second. But after one doubling cycle, the dots will now be twice as far apart, which means they'll be receding at 20 pixels per second instead of 10. Those dots have accelerated, even though the doubling rate is constant. The same thing happens with distant galaxies in our universe. Remember, the speed of these galaxies is distance dependent. If the distance doubles, so does the speed. It's just like the circle. In the far future, the doubling rate will be constant, once every 14 billion years. And since that expansion carries all the stuff with it, distant galaxies will be twice as far apart after those 14 billion years, which means they'll be receding twice as fast. A constant doubling rate results in accelerating objects. So what does the dark energy actually do? It keeps the doubling rate above zero forever. Without dark energy, the doubling rate would eventually settle at zero. In other words, space would stop doubling. Dark energy provides a minimum value that's not zero. That's it. If you're still having trouble wrapping your head around this, here's one last thing to keep in mind. Space is not accelerating. Acceleration is a measure of motion, but space isn't going anywhere. There's just more of it over time. It's the stuff inside that space that accelerates. Dark energy doesn't cause that acceleration. It just maintains it. Because that type of growth is natural for a universe. But here on Earth, that kind of natural balance is fading. Our ecosystems aren't accelerating, they're collapsing. And they need us to maintain them. That's where my friends at Planet Wild come in. They're a community of 14,000 people that crowdfund meaningful conservation projects. From protecting our oceans to reviving forests and saving endangered species. They document all their projects in video reports that you can find right here on YouTube, so you can see what your contribution helped achieve. For example, in one of their recent projects, they rescued orphan seal pups in the Baltic Sea. What impresses me most about Planet Wild is how transparent the organization is. Their videos and the reports on their app show you exactly how your membership is making an impact, and how much we can achieve together if we pool our resources. They even release a yearly financial report so you can see how the money was used. If you want to be a part of this community and support real solution-focused conservation, become a Planet Wild member. You can give what feels right. Every contribution makes a difference for the planet. The first 100 people who sign up using my code, Asylum10, will get their first month covered by me. Scan the QR code or click the link in the description. And don't worry, you can cancel anytime, no questions asked. Check out the link on the end screen to see Planet Wild's seal pup rescue. It's a hopeful reminder that together we can make a huge difference for nature. And until next time, remember, it's okay to be a little crazy. Feinstein 1004 asked, aren't Kepler's laws just another form of angular momentum conservation? Well, you can derive all 3 of Kepler's laws from Newton's laws, and one of them will give you angular momentum conservation. But Kepler didn't know that because Newton wouldn't show up for several more decades. Anyway, thanks for watching. It's glitter, it's like smallpox.